February 1945, and the morning air above Bochum Work Test Facility, near Stuttgart, carries the acrid smell of hydrogen peroxide and concentrated nitric acid, while engineers prepare what appears to be a telephone pole with stubby wings strapped vertically to a 40-foot steel tower, and, inside, a cramped wooden cockpit, barely larger than a bathtub, sits Lothar Sieber, a 25-year-old Luftwaffe test pilot, who has exactly 90 seconds before 4,400 pounds of thrust hurl him skyward at accelerations that would render most men unconscious, and his mission brief outlined just 3 hours earlier is simple in theory, but apocalyptic in execution. Ignite the Walter rocket motor. Climb vertically to 30,000 feet at 600 miles per hour, close to within 30 meters of an Allied bomber formation. Fire 24 unguided Henschel rockets in a single salvo, separate the nose cone via explosive bolts, deploy a personal parachute, and pray the tumbling fuselage does not strike him during descent, and the entire sequence from launch to landing must occur within 7 minutes, because that is precisely how long the fuel supply will sustain combustion before the aircraft becomes a powerless wooden glider falling toward Earth. And Sieber knows what the engineers will not say aloud, which is that the survival probability hovers somewhere near 20%. And the reason he occupies this death trap bolted to a tower stems not from courage or patriotism, but from the mathematical certainty that without something this desperate, the entire Reich will disappear under 10,000 tons of Allied bombs, dropping nightly on cities that no longer possess the fuel fighters or pilots to mount effective defense against the 1,000 bomber streams. Blackening German skies. The weapon strapped to that launch tower was designated Bachem Ba 349 Natter, meaning Viper in German, and it represented the absolute terminus of aircraft design philosophy, where conventional aeronautical engineering principles were discarded entirely in favor of a guided missile with a human guidance system, and the concept emerged from the fertile desperation of late 1944, when Reichsmarschall Hermann Göring gathered what remained of Germany's aviation engineers at Lechfeld Airfield and presented them with an impossible equation. Allied bombing raids now fielded over 1,000 heavy bombers per mission, protected by 500 escort fighters, while Germany could barely launch 50 interceptors due to catastrophic fuel shortages, pilot attrition, and the destruction of aircraft factories themselves, and conventional interceptors like the Messerschmitt Bf 109 required 200,000 Reichsmarks to manufacture consumed precious aviation gasoline by the hundreds of liters, needed trained pilots who took 18 months to produce demanded concrete runways that Allied bombs cratered nightly and arrived at engagement altitude 15 minutes after scramble, by which time bomber formations had already released ordnance and turned for home. And Göring's question was brutally direct. Design something expendable that Hitler Youth can operate with minimal training, that costs almost nothing to build, that requires zero runway infrastructure, that reaches combat altitude in under 2 minutes, and that can destroy multiple bombers in a single attack run before the pilot bails out. Every engineer in that room understood he was describing a manned surface-to-air missile, not an aircraft. But the alternative was watching Germany's cities burn while the Luftwaffe sat grounded for lack of fuel. Standard interceptor tactics in 1944 achieved operational altitudes of 30,000 feet, approximately 12 to 15 minutes after scramble, consuming roughly 300 liters of aviation gasoline per sortie, delivering perhaps 2 fighters per raid due to fuel allocation, limits which provided firepower equivalent to maybe 40 cannon shells against bomber formations, carrying thousands of tons of explosives, and the mathematical futility was obvious, because even with perfect accuracy and unlimited ammunition, 2 fighters engaging 1,000 bombers represented a loss exchange ratio that guaranteed Germany's destruction. Within months, and British Spitfire interceptors climbing from Dover to 30,000 feet required 14 minutes, American P-51 Mustangs needed 16 minutes, and Soviet Yak-3 fighters took 18 minutes, meaning conventional interception doctrine everywhere relied on early warning networks, radar tracking, and sufficient fuel reserves to maintain standing patrols. And Germany in 1945 possessed none of these advantages, have lost radar stations to advancing Allied armies' petroleum, refineries to strategic bombing, and the luxury of time to physics itself, because Allied bombers crossing the Rhine gave defenders perhaps 20 minutes warning before ordnance release over industrial targets. The solution originated not from established aviation firms like Messerschmitt or Focke-Wulf, but from a small furniture manufacturing company called Bockum Verka in Waldsee, led by aeronautical engineer Erich Bockum, who had previously worked on tail-sitting vertical takeoff concepts for Fiesler during the 1,930 seconds and understood that abandoning horizontal flight entirely could eliminate 90% of an interceptor's complexity. And when SS Obergruppenführer Hans Kammler, who controlled all secret weapons development, visited Bockum's facility in October 1944, he saw detailed plans for an aircraft that was barely an aircraft at all, but rather a piloted rocket with enough stability to aim itself at bombers before the human component ejected, and Bockum's engineering philosophy rejected every conventional wisdom. No landing gear because it would never land. No forward visibility because the pilot aimed via instruments. No metal construction because wood was plentiful. No pressurized cockpit because the flight lasted only minutes. No ejection seat because explosive nose separation was simpler. And most radically, no horizontal takeoff because vertical launch from a rail eliminated the entire concept of runways, and Kammler immediately allocated resources, not because the design was safe or even sane, but because it was the only proposal that addressed Germany's actual constraints, which were not engineering limitations, but resource depletion on a civilizational scale. Construction began at Bockum Werke Sankt Leonhard facility in November 1944, using materials that reflected Germany's collapsing industrial base. Fuselage sections built from laminated spruce plywood, bonded with phenolic resin, because aluminum was reserved for jet engine production wings constructed from plywood, stressed skin over wooden spars because metal fabrication required machinery diverted to tank production tail surfaces cut from 3mm plywood sheet because even steel tubing had become scarce, and the Walter HWK 109-509 rocket motor, originally developed for the Messerschmitt Me 163 Comet interceptor, which generated 2,000 kilograms of thrust for 470 seconds by combining T-Stoff hydrogen peroxide at 80% concentration with C-Stoff hydrazine hydrate catalyst, creating superheated steam and nitrogen gas, exhausting through a de Laval nozzle at velocities approaching 3,000 meters per second, and the entire launch sequence was placed, automated, using a mechanical timer that ignited 4 Schmitting 109 to 533 solid fuel booster rockets mounted around the fuselage base, producing an additional combined 2,400 kilograms of thrust for 12 seconds to achieve initial acceleration before jettisoning at 1,500 meters altitude. When the main Walter motor sustained vertical climb, and this dual-stage propulsion system allowed the Natter to achieve 600 kilometers per hour velocity within 10 seconds of tower release and reach combat altitude of 9,000 meters in precisely 93 seconds compared to conventional fighters requiring 12 to 15 minutes, and the engineering elegance lay not in sophistication, in ruthless simplification, because every component served exactly one function, with zero redundancy, and failure meant death. But success meant possibly 3 bombers, destroyed per sortie at a manufacturing cost of 5,000 Reichsmarks, which was 40 times cheaper than a Bf-109, and the brutal calculus suggested that even with 80% pilot mortality rates, the exchange ratio favored Germany if each Natter killed just 1 bomber. When launched, the Natter pilot experienced 17 gravities of acceleration during the 12-second booster phase, which was beyond human tolerance without specialized equipment. So Bockum engineers installed a crude glycerin-filled bladder seat that distributed force across the pilot's back and a padded headrest that prevented cervical spine fracture during the initial thrust surge, and the cockpit instrumentation consisted of exactly 7 items: an altimeter measuring up to 10,000 meters, a climb rate indicator showing vertical velocity, a simple gun sight connected to the armament bay, a compass for orientation after nose separation, a timer showing elapsed seconds since launch, a lever for manual nose cone separation if automatic, pyrotechnics failed, and a parachute ripcord painted bright red, and the pilot's task, during ascent, was to maintain vertical orientation, using rudimentary stick controls, connected to aerodynamic surfaces that provided minimal authority at low speeds, but became effective above 300 kilometers per hour, and at 9,000 meters altitude, when the Walter motor began consuming its final reserves. The pilot would observe bomber formations visually through a small armored glass panel and maneuver to intercept heading, using those vestigial control surfaces, and at a range of 100 meters or less, he would trigger the armament bay, containing 24 Henschel Hs, 217 Phone, 73mm unguided rockets, arranged in a honeycomb pattern, each carrying a 500-gram hexagon high explosive warhead, and the entire salvo would ripple fire in 1.2 seconds, creating a shotgun blast of projectiles traveling at 450 meters per second, designed to saturate a bomber's defensive volume rather than achieve precision. Because at closing velocities exceeding 800 kilometers per hour, aimed fire was impossible. And immediately after rocket discharge, the pilot would pull the nose separation lever, triggering 4 explosive bolts rated at 12,000 newtons shear strength that severed the forward fuselage section containing the empty armament bay and wooden nose cone, allowing it to tumble away, while the aft section containing the pilot decelerated rapidly due to increased drag, and at this point, the Walter motor would have exhausted its fuel supply, and the pilot was instructed to count to 3, allowing sufficient separation from debris before deploying his personal parachute from a backpack harness, and the remainder of the aircraft, including the valuable rocket motor, would deploy its own recovery parachute, triggered by a barometric switch calibrated to activate at 4,000 meters altitude, allowing recovery teams to salvage the engine for refurbishment and reuse. And this entire sequence, from tower launch to dual parachute deployment, was calculated to require between 6 and 7 minutes depending on altitude at interception. The first unmanned test launches began in November 1944 at Heuberg Military Training Ground, using concrete ballast in place of a pilot, and initial results were catastrophic, with 3 consecutive vehicles disintegrating during booster separation when aerodynamic loads exceeded structural tolerances of the plywood airframe, and engineers reinforced wing root joints with steel brackets and thickened tail surface plywood from 3 to 5 millimeters, which added 8 kilograms to empty weight, but prevented structural failure during transonic acceleration. And by December, 1,944 unmanned launches were achieving target altitudes reliably, and recovery parachutes were deploying correctly, and telemetry data suggested the vehicle could sustain the planned flight profile. And on the 28th of February, 1945 at Kirchheim Unter Tech Test Facility, Lothar Sieber climbed into Natter prototype M23 for the first manned vertical launch in aviation history, and the tower crew locked the fuselage to the launch rail and connected umbilical lines supplying electrical power and compressed air to actuate control surfaces, and Sieber completed his abbreviated checklist and signaled readiness, and the launch controller initiated the automatic sequence, and the 4 Schmitting boosters ignited simultaneously, generating a sound described by witnesses as resembling continuous thunder, and M23 accelerated up the 40-meter rail in just over 1 second and cleared the tower at 120 kilometers per hour, and continued vertical ascent, trailing white exhaust, and then at precisely 1,500 meters altitude during booster separation, something catastrophic occurred, and eyewitnesses reported the cockpit canopy detaching completely and tumbling earthward, while the Natter continued climbing without deviation for another 2,000 meters before entering an uncontrolled inverted spin and impacting terrain at terminal velocity and recovery. Teams found Lothar Sieber's body 300 meters from the impact crater, and the post-mortem investigation concluded that the canopy locking mechanism had failed catastrophically when booster jettison created an asymmetric aerodynamic shockwave that imparted lateral force to the canopy hinges exceeding their design load by a factor of 8, and the sudden decompression at 1,500 meters altitude, traveling at 500 kilometers per hour, had effectively decapitated Sieber, and the program was immediately suspended, pending redesign. Bockum engineers completely eliminated the canopy mechanism in subsequent prototypes, replacing it with a fixed wooden fairing with only a small reinforced glass viewport, because the pilot needed visibility only during the final attack phase, not during ascent, and this modification added structural rigidity while removing the failure point that killed Sieber. And by mid-March 1945, 3 additional unmanned tests validated the new design, and approval was granted for resuming manned trials. But by this point, Allied armies were crossing the tests validated the new design. Rhine and the strategic situation had deteriorated to the point where natter deployment became militarily irrelevant because the bomber formations it was designed to intercept were now launching from airfields in Belgium and Holland, barely 200 kilometers from targets, giving defenders only minutes of warning, and the launch infrastructure required for natter operations, including vertical towers, fuel storage, and trained ground crews, could not be relocated quickly enough to follow the collapsing front lines, and production was officially terminated on April 4, 1945. After 36 complete airframes had been assembled at various facilities, including Bochum St. Leonhard Waldsee facility, and several subcontractors in the Black Forest region, and none ever engaged Allied aircraft in combat. In March 1945, during Operation Varsity, the Allied airborne assault across the Rhine, elements of the U.S. Ninth Army captured an intact natter launch site near Kirchheim, complete with 4 assembled aircraft ground support equipment, technical manuals, and interrogated Bockum engineers, and the immediate intelligence assessment filed with Supreme Headquarters Allied Expeditionary Force described the weapon as representing a conceptual leap beyond current Allied thinking, particularly regarding vertical launch manned interceptors, and within weeks, the captured vehicles and documentation were shipped to Wright Field, Ohio, for evaluation by Army Air Force's Technical Intelligence, and the American analysis concluded that while the natter itself was too dangerous for operational use, the core concept of vertically launched rocket-propelled interceptors had significant merit for future air defense applications, particularly against high-altitude jet bombers that were anticipated in coming decades, and British intelligence officers from the Royal Aircraft Establishment, Farnborough, conducted parallel assessments of captured examples and noted that the Walter rocket motor technology vertical launch rail system represented areas where German engineering had advanced beyond corresponding British programs, and both Allied powers initiated classified research programs based on captured natter data, and by 1947 American engineers at Bell Aircraft were developing the X-1 rocket plane, using modified Walter motor principles and vertical launch concepts tested in the XF-91 Thunderceptor program, and the Soviet Union reverse-engineered complete Walter motors from captured stocks and incorporated them into early surface-to-air missile designs, including the S-25 Berkut system deployed around Moscow in 1955. And the direct lineage from natter to Cold War vertical launch missiles is documented in declassified correspondence between Werner von Braun, who supervised natter evaluation at Peenemünde before its capture, and American rocket engineers at Redstone Arsenal, who explicitly cited Bockem's work in developing Saturn launch vehicle staging mechanisms. Allied assessment of comparable interceptor programs revealed the profound technological gap the natter attempted to bridge. The British de Havilland Mosquito night fighter achieved operational ceiling of 11,000 meters in approximately 18 minutes, consuming 420 liters of aviation fuel per sortie, and delivering 4 20mm cannon with combined ammunition load of 240 rounds, which provided approximately 12 seconds of sustained fire, and its wooden construction, similar to natter's, reflected British timber expertise, but served entirely different operational doctrine, emphasizing endurance and precision rather than sprint interception. And the American Northrop P-61 Black Widow night fighter reached 10,000 meters altitude in 22 minutes, burned 630 liters of fuel per sortie, and carried 4 forward-firing 20mm cannon, plus 450 caliber machine guns in a dorsal turret, providing substantial firepower, but requiring extensive ground infrastructure including 3,000-meter concrete runways, maintenance crews of 12 personnel and pilot training periods exceeding 200 hours, and Soviet Lavochkin La-7 fighters operating in air defense roles achieved 9,000 meters altitude in 16 minutes, consumed 280 liters of fuel, and armed with three 23mm cannon, but similarly depended on functioning airfield infrastructure, radar, early warning, and trained pilots. And when compared directly, the Natter achieved 9,000 meters in 93 seconds, 1/10 the time required by Allied equivalents, consumed 80 liters of fuel. 1/4 the Allied average, cost 1/40th the price of conventional fighters, and required pilot training measured in hours, not months. And the trade-off was, of course, that it was essentially a suicide weapon, where pilot survival depended on perfect execution of 7 critical steps during 6 minutes of flight, and any single failure meant certain death. But from Germany's perspective in 1945, these were not deterrents but acceptable costs, because they still possessed young men willing to die, but no longer possessed fuel, runways, or time. Production. Documentation recovered from Bachem facilities indicates that manufacturing one Natter required approximately 120 man-hours of labor, primarily woodworking and assembly, compared to 1,800 man-hours for a Bachem. 109 fighter and materials cost breakdown showed fuselage, plywood sections, totaling 600 Reichsmarks. Walter rocket motor, 1,200 Reichsmarks, when newly manufactured, or 300 if refurbished from Me. 163 stocks booster rockets, 800 Reichsmarks. Avionics and instruments, 400 Reichsmarks. Armament bay and phone rockets, 1,000 Reichsmarks. And miscellaneous hardware, including explosive bolts, parachutes, and control linkages, totaling 1,000 Reichsmarks for an all-inclusive unit cost of 5,000 Reichsmarks compared to 200,000 for conventional fighters, and projected production capacity, if the war had continued, suggested Bachem could manufacture 50 Natters per week using existing facilities. And if satellite workshops were established throughout the Black Forest region, where timber and woodworking expertise were abundant, capacity could expand to 200 per week by summer 1945, and operational planning documents proposed deploying Natter launch sites in networks of 4 towers, spaced 500 meters apart, with centralized fuel storage and targeting coordination provided by remaining Freya radar installations, and each site would maintain 8 aircraft, allowing 2 waves of 4 interceptors launched in rapid sequence against bomber formations, and pilots would be drawn from Hitler-Jugend volunteers, given 3 days of ground training on a wooden mock-up, followed by 1 live launch, with the understanding that survival rates would improve with experience. But first, mission fatality probability was estimated at 70%, and the program's architects, including SS Obergruppenführer Kammler, calculated that even with these catastrophic losses, each Natter sortie that successfully engaged bombers would destroy an average of 2 aircraft based on the saturation effect of 24 unguided rockets fired at close range into dense formations, and at this exchange ratio 50 Natters per week would inflict 100 bomber losses weekly, which exceeded the 8th Air Force's sustainable attrition rate, and might force a reduction in bombing tempo. But of course, these calculations assumed launch sites could remain operational under Allied air superiority, which by March 1945 was an absurd premise. Surviving Natter examples reside in exactly 3 museum collections worldwide. One nearly complete BA 349A airframe at the Deutsches Museum in Munich, recovered from Bachem St. Leonhard facility in May 1945, missing its Walter motor, but retaining original armament bay and wooden construction details. 1. Partial fuselage section, with attached booster rockets at the National Air and Space Museum, Stephen F. Udvar-Hazy Center in Virginia, acquired from U.S. Army Aberdeen Proving Ground in 1978. And 1 restored composite example at the Aerospace Museum in Belgrade, Serbia, assembled from components captured by Yugoslav partisans near Austria in April 1945. Technical documentation, including original Bachem engineering. Drawings exists in Bundesarchiv Militärarchiv Freiburg files, RL 3/2847 through 2851, and in U.S. National Archives Record Group 242 captured German documents collection and the complete Walter HWK 109 to 509 motor. Technical manual survives in English translation as U.S. Air Force Technical Report, FSU 1122ND, filed at Air Force Historical Research Agency, Maxwell Air Force Base, and patent records show Erich Bachem filed German patent DE 767829 on December 12, 1944 for Verfahren und Vorrichtung zum senkrechten Start von Flugzeugen, meaning method and apparatus for vertical aircraft launch, which was never granted due to the Reich's collapse, but the concept itself entered public domain and influenced post-war missile development across 3 continents. If you are finding this examination of desperate German aerial innovation compelling, subscribing helps this channel continue exploring the obscure weapons and engineering extremes that emerged when conventional warfare became impossible and resources dwindled to nothing but human willingness to die remained abundant. The psychological impact on Allied bomber crews, had Natter reached operational deployment, can only be estimated from contemporary intelligence assessments and post-war strategic bombing surveys, indicate that even the threat of new German wonder weapons created measurable anxiety among flight crews, particularly following the introduction of Me-262 jet fighters in late 1944, which could engage bomber formations with near impunity, and aircrew debriefing reports from early 1945 document increasing discussion of rumored German suicide weapons, including reports of piloted V-1 flying bombs and kamikaze-style ramming attacks, and had Natter attacks actually occurred, with pilots deliberately ramming bombers after expending rockets, the psychological effect would likely have mirrored the impact of Japanese kamikaze attacks on U.S. naval personnel in the Pacific Theater, where the certainty of facing suicidal adversaries created pervasive dread that exceeded the actual casualty rates, and moreover the vertical launch capability would have introduced a new tactical problem, because existing bomber defensive doctrine relied on early warning from escort fighters and formation defensive fire, but a Natter launching from directly beneath a formation would appear with only seconds of warning, rising at 600 kilometers per hour from ground level to combat altitude faster than any defensive response could engage it, and this would have forced fundamental changes in bombing approach patterns, possibly requiring higher altitudes which reduced accuracy, or dispersed formations which reduced defensive firepower concentration, and these tactical adaptations would have degraded bombing effectiveness even without achieving significant aircraft kills, demonstrating that the Natter's greatest potential impact was not kinetic, but psychological and operational. The engineering principles pioneered in Bachem's desperate vertical launch system directly influenced American missile defense concepts throughout the 1,950 seconds, particularly the Nike Ajax and Nike Hercules surface-to-air missile systems, which employed vertical launch from fixed sites using solid fuel boosters for initial acceleration, followed by liquid fuel sustainers for target interception, and the concept of rapidly responding vertical launch point defense against high-altitude bombers became doctrinal for both American and Soviet air defense networks, and NASA's Project Mercury launch escape system, which used a solid fuel rocket tower to extract astronauts from failing boosters, employed the same explosive separation concept that Natter used for nose cone jettison, and the vertical launch infrastructure developed for Minuteman intercontinental ballistic missiles in the 1,960 seconds, including silo construction, rail guidance systems, and rapid fuel loading procedures, all traced conceptual lineage to Bachem's work and declassified U.S. Air Force historical studies, including German Guided Missile Development, published by Air Materiel Command in 1946, explicitly credited Natter as demonstrating the feasibility of vertically launched manned interceptors, and recommended continued research into point defense systems using similar principles, though without the human pilot. And by the 1972, every major military power operated vertically launched missile systems, and wooden rocket strapped to a tower in February 1945 had become the grandfather of an entire class of weapons. Total Natter production reached exactly 36 complete airframes between November 1944 and April 1945, with an additional 14 incomplete fuselages found at various workshops when Allied forces overran production areas. And of the 36 complete examples, 22 were expended in unmanned test launches. 3 were destroyed during Allied bombing of storage facilities. 1 killed its pilot during the sole manned test flight, and 10 were captured intact by American, British, and Soviet forces, and none ever engaged enemy aircraft in combat, making the Natter perhaps the most extensively developed weapon system that saw zero operational use. And the reasons for this failure were entirely external to the weapon itself, because the engineering worked as designed, and test launches demonstrated the capability to reach intercept altitude and deliver ordnance. But the strategic situation had deteriorated beyond the point where point defense weapons could affect outcomes, and the Reich that conceived Natter as salvation no longer controlled the territory necessary to deploy it effectively, and the radar networks that would provide targeting data had been destroyed or captured, and the fuel supply chains necessary to sustain operations had been severed by advancing armies, and most critically, the temporal advantage Natter was designed to provide, reaching intercept altitude in 90 seconds, became irrelevant when Allied bombers launched from bases 200 kilometers away, giving total flight times of 15 minutes, meaning even instant response could not prevent ordnance delivery. And this represented the fundamental futility of wonder weapons in Germany's final months, where innovation continued accelerating, even as the industrial and territorial base necessary to exploit those innovations disappeared. February 1945, and Lothar Sieber sits in a wooden cockpit atop a tower, waiting for ignition, while engineers who know this is murder, dressed as test flight, check connections for the final time, and the Walter motor that will hurl him skyward burns with chemicals that could dissolve flesh, and the rockets he will fire at bombers, assuming he survives, ascent have never been tested against actual targets, and the parachute that should return him to Earth works only if 7 other systems function perfectly before it, and he signals readiness anyway because he understands what the engineers understand, which is that Germany no longer has choices, only increasingly desperate gambles against physics and time. And the entire Natter program represented the terminal logic of technological warfare, where innovation becomes indistinguishable from suicide and engineering genius serves only to make dying slightly more efficient. And when that tower released its wooden rocket into the sky, it carried more than one pilot, but the last fragments of the belief that Germany could invent its way to survival. And when Lothar Sieber's body struck Earth 300 meters from the crater, it proved what everyone already knew, which was that desperation is not a design philosophy, and rocket motors cannot reverse strategic collapse, and the most sophisticated engineering cannot compensate for having already lost the war. And that was German aviation in 1945. Brilliant, desperate, and utterly futile, where wooden rockets strapped to towers represented the best remaining option, and young men volunteered to ride them skyward, knowing they would likely never return, because the alternative was watching everything burn from the ground. And at least this way they died doing something that looked like fighting, even though it was really just falling with extra steps in fire.